Hello, welcome to Picture Me Coding with Eric Aker and Mike Mull. Hello, Mike. Welcome back to town.
Hey there. It's nice to be back in Southern California.
Nice foggy morning for us. Huge surf out there somewhere booming in the ocean. Mike, sometimes you and I get off on these topics that are distributed systems topics. And I have this feeling of like, you ever see that movie Dawn of the Dead where there's a bunch of weird shit that happens at the beginning and then they get in a helicopter and they like fly around looking for a safe place? And then they see a mall and they go and they live at the mall. It's kind of like that. Like, where you get into these problems in distributed systems and it's like they're just overwhelming. It's like the zombie hordes. And then you see a nice, safe mall and you go, oh, that'll solve it. I'll go hide out in that mall and the zombies won't get me. I think about this all the time, actually. It sounds like a weird, strained metaphor. I'm not lying. This is actually, it pops in my head all the time.
I think the metaphor may be slightly different in the zombie movie scenario than the distributed system scenario, but
Yeah, they all have different metaphors, right? They go live in the mall and they're like, the mall will solve all of our problems. There's food at the food court and there's sports equipment for when we get bored and a movie theater. And it turns out to be this big commentary on buying shit. So, Mike, I was working on one of my personal projects over the last couple weeks. This is an open source project. I just do it for fun. I'm not trying to build it for anybody else to use. I just build it as a thing that I like a puzzle for me to solve. And it's like a service that I built that has other puzzles kind of embedded in it. And the puzzles tend to be distributed systems puzzles. It's this little thing I wrote in Rust just for fun, really. That's all it is. And I wanted to add a feature to it. And as I started working on this, I thought, wow, this might be a good use case for CRDTs. CRDTs, I know we talked about before. That stands for conflict-free replicated data type. But my initial reaction was, well, that sounds complicated. I don't really feel like doing that. This is this hobby project. I don't really want to get into CRDTs for it. And I don't know what happened, but I started reading something and it like triggered this flood of, I had this like illuminatory moment like, oh, wow, I think I get it in a way I never got it before. And I started reading all these papers and I started reading different blog posts. I started reading code where people are implementing these things. And I got really, really fascinated by CRDTs. So that's what I wanted to talk to you about today, Mike. When I first started looking at CRDTs, I thought, okay, these are just data structures, right? The idea is that it's a data structure that can be used in a distributed system, and guarantees that you'd like your system to have can be kind of encoded in the data structure so that when those data structures get shared in the distributed system, they, in a kind of maybe magically sounding way, sort of resolve conflicts. They get you to some form of consensus, which we talked about before with distributed systems. Do you have an informal idea of what a CRDT is before we started doing this work this week?
very informal. I think of them as basically data structures where, to some extent, the order of operations doesn't matter. Having read through the papers now, I see that that's sort of true, but maybe not entirely true.
I mean, I thought I had even the wrong impression that I thought it was like any arbitrary data structure could be a CRDT if you just do something to it or add some interface to it. And that's actually not the case. So we started reading a couple different papers and some other pieces that kind of augment this information. There's been a lot of research published on CRDTs over the last 15 years. First described around 2007, 2009. And one of the key contributors of these is a guy named Mark Shapiro. He's in Europe at INRIA. In 2011, Shapiro and his co-authors wrote a paper called Conflict-Free Replicated Data Types. And that's a shorter paper, probably a conference paper. It's about 20 pages. And then that same year, they wrote this long 50-page paper called A Comprehensive Study of Convergent and Commutative Replicated Data Types, where they talk about CRDTs, talk about their goals, and then they describe specific CRDTs that they have dreamed up. And the interesting thing is, like, that's the list pretty much that everybody goes by. There's like a dozen of these data structures described in the comprehensive paper. And That's pretty much it. There aren't a lot. There aren't like other data structures that people have described that are CRDTs really outside of this paper. So informally, we can think of CRDTs as these data structures that can be combined in ways that make them converge in a distributed system. I want to come back to that word convergence. Why would we want to do this? Let me give you a little chunk from their shorter paper's introduction. They write, when network delays are large or partitioning is an issue, as in delay tolerant networks, disconnected operation, cloud computing, or P2P systems, eventual consistency promises better availability and performance. An update executes at some replica without synchronization. Later, it's sent to other replicas. All updates eventually take effect at all replicas asynchronously and possibly in different orders. That sounds pretty cool. Concurrent updates may conflict. Conflict arbitration may require consensus and a rollback. They talk about how this is weaker consistency. They say, you know what? This is okay for some applications, but resolving the conflicts is pretty hard. And so they say, well, the previous literature doesn't tell us much. They offer little guidance on designing a correct, optimistic system, and ad hoc approaches are brittle and error prone. And they describe how in the Dynamo paper at AWS, they had these examples of the concurrency anomalies of the Amazon shopping cart where stuff would be added to the cart and then it would disappear and then later it would appear again. And so Dynamo is an eventually consistent system. And so they write, we propose a simple, theoretically sound approach to eventual consistency. So I want to pause here and just focus on some of the terms that they're using. The first is eventual consistency. So this is AP, not like a Raft or a Paxos or like we definitely want to have consensus before proceeding. Not like a relational database with two-phase commit. This is like eventually we'll work it out, right? That's cool.
I'm sure you'll bring it up, but they do talk about strong eventual consistency.
That's what I wanted to say. Yeah. So you hear eventual consistency, think, okay, we're in. I mean, going by CAP theorem, it's consistency, availability, partition tolerance. We're in the availability and partition tolerance quadrant of CAP theorem. We're in AP systems. But they say we are talking about strong eventual consistency, not just eventual consistency. This is like the next paragraph in the introduction here. They say our system model, strong eventual consistency, avoids the complexity of conflict resolution and of rollback. Conflict freedom ensures safety and liveness despite any number of failures. It leverages simple mathematical properties that ensure absence of conflict, monotonicity in a semi-lattice, and our commutativity. A lot of heavy words in there. What do you think so far based on what they write in this introduction?
It is an interesting idea. It's easy to get a little confused, though. First of all, they call these things two different things at different points in time. So I think in the original paper, they use commutative replicated data type.
Well, there's commutative and convergent.
And they use commutative, but in the later papers, they're called conflict-free replicated data types. So they've got multiple names for the same thing, and I think it was just a case of, their ideas about what they were doing evolved, and so they tried to keep the same abbreviation, but make it more appropriate to the general scheme. The other thing is that this idea of the operation-based versus the state-based. Even though they show in one of the papers that the two things are equivalent, I found it a little bit difficult to reconcile in my mind that they are doing the same things because they seem like they would require considerably different mechanisms to work. But
well, I want to get to that in a second. Let me give you like my sort of naive, informal gloss on what they're talking about here. And I want you to listen to my naive, informal gloss and say if I'm close enough or if I'm too informal and messing it up. What they're saying is we can describe some data structures that just by using them, they kind of internally resolve conflicts when you send them around in a distributed system. And those data structures, they really have to follow certain mathematical properties to really work. But the cool thing is that if they do follow those mathematical properties, they will achieve strong eventual consistency. And it actually doesn't matter how many failures. If you look at like a Paxos, you look at the Paxos paper, Lamport's like, and there are earlier proofs about this. If you have 5 machines, Paxos can tolerate up to, n number of failures, where n is like two. Two of those could fail. So it's like you need to, if you want to tolerate 8 failures, you need 2 times 8 plus 1 machine. You need 17 machines, right? And here they're talking about any number of failures, and it doesn't matter what order the updates are received in. And it's really a data structure problem, not a first I do this, then I do that, then I reserve a commit, then you do that. It's not a complicated protocol. You design a data structure, it has certain mathematical properties, and you get strong eventual consistency. That sounds pretty rad. Is my informal too? Am I overselling it?
No, I don't think so. I think it is pretty rad. I think that's why it comes up so frequently in the local first software paradigm, because it does have this idea that even with pretty significant network failures or network unavailability, you can still eventually reach some sort of consistent state, which is, a very desirable thing.
You compare it to something like Raft. In Raft, it's a leader-based system. Raft, pretty cool. Raft, of course, linearizable, right? So it's like very, very strong consensus in Raft. But Raft, sometimes the leader blows up or whatever, and the cluster has to elect a new leader. There's one leader, and all the requests have to go through that one leader. So it's a little bit of a bottleneck. And if you need to elect a new leader, you got to wait around until the new leader shows up and starts working properly before you could send updates into that cluster. It is possible for Raft to get into a situation where it's repeatedly electing leaders, and the randomness makes it highly unlikely that it would do that forever. But everything goes to the leader. And what they're describing here in this CRDT paper is they're saying our strong eventual consistency means that a replica in the system is always available for reads and writes independently of network conditions. Even if the replica is not online with the rest of the cluster, you can send stuff in. That's pretty rad. Any communicating subset of replicas of a strong eventual consistency object eventually converges, even if partitioned from the rest of the network. That's pretty cool.
It's pretty cool. I get what they describe more solidly in the state-based version, though, because I can see directly there how it's related to orderings. When it's described in the state-based version, I feel like I sort of intuitively get what the trick of it is, but in the operation-based ordering, it feels like there's some mechanism that's being required but not described in detail.
So maybe we should talk about that distinction first. So they use this word converges a lot. I think maybe we should take a little pause here and talk about what converging is all about. They're using that in a math. Well, we have to talk about mathematical, because they keep saying if you have the data structure and it has these mathematical properties, right? It satisfies these mathematical properties, it will converge, and you can use it as a CRDT in a cluster. And then there's a distinction between state-based and operation-based. Okay, so where should we go first, do you think? In the 50-page comprehensive paper, they use the term commutative replicated data type and convergent replicated data type. And these terms fell out of favor like shortly after this paper. Now everyone talks about state-based and op-based. Their convergent in the paper is state-based. And the commutative in the paper is operation-based. So here's the idea. A state-based CRDT, in its state somehow, the whole state of the data structure, it keeps a history, kind of what has happened for each node And you could just sort of share that entire data structure around an entire cluster, and other nodes will know how to, and this is the term, they'll know how to merge another replica's state in with their state. And that merging will satisfy certain properties in order for it to be a full state-based CRDT.
So I get this idea, and I guess we should also emphasize the R in the CRDTs. So the the sort
The
of idea
replicated.
here is that you have this same data type on multiple replicas, and the objective is to keep them in sync, or at least eventually in
Yeah.
sync. Um,
Well, yeah. So, like, consider like the so one of the ones I talk about in the comprehensive paper and the earlier paper is the G counter, which stands for grow only counter. Um, so you could imagine something like I want to keep track of how many users are actively using my website, and maybe my website's massive, so I can't just store that on a single computer. I want it on a few to be more reliable in case one of them crashes or whatever. But the currently using means I have to decrement. Somebody shows up, they're actively using it, I add one. That person leaves or just doesn't refresh the page in a while, I have to subtract one. Now, how can I do that in a group of machines? Because the adding and subtracting, like each different server has got to know what the other servers know. That's a bit of a problem because there's a little bit of delay in communicating that knowledge. And when they're adding and subtracting numbers, they have to somehow agree. In the paper, they talk about how it has to converge. So a state-based version of this would probably have a counter for each node, and the state-based operation would say, Mike, your counter for these three servers is server A 0, server B 0, server C 1, right? So your request showed up at server C, so that's the counter. How many requests? One. You add all those numbers together. And you could take that data structure and you could share it with the other servers. And if you share it with server B, and server B receives a request, now it's one on B and one on C. Total is two. But notice we're not just taking a single number and adding and subtracting or whatever. When B notices you're no longer there, it decrements. But you may have some weird, like, these moments in time. This is eventual consistency where the number doesn't quite completely reflect what's going on, but it's going to get there. It's going to converge. So state-based CRDT is you take that whole state, you share it around the cluster, and you can merge it across replicas and get something that still makes sense. Operation-based is what it sounds like. Instead of sharing my data structure of the counts for each server, instead what I do is I say, Mike, server C, and server A, I want to add one. I'm server B. And if we have certain guarantees about those operations as they're getting shared, then that also forms a CRDT. So that's operation based. Add one versus state based. Here's my current count, my current state. How'd I do? Does that make sense?
yes, I think so. But this is also where I get confused, or not, maybe not confused, but so I think I get the state-based ones to a certain extent. There's a there's an idea related to ordering in here that I find useful and sort of satisfying. So I think you mentioned this term from the paper already, but they talk about lattices. And so
Mm-hmm.
the lattice here is a mathematical term. It's a sort of algebraic structure that if you have an ordered set, usually in our case, we're talking about partial orders, but if you have an ordered set, then a lattice is something where any two elements in that partial ordering have what they call a least upper bound. And also in a
Mm-hmm.
true
Mm-hmm.
lattice, they would also have a greatest lower bound. In in the CRDTs, we only care about the least upper bound.
Semi
Yeah, so
lattice,
they
right?
call
It's
it
a semi lattice. They only care about the
right, and
converging point.
they call this a semilattice, and they use the term join semilattice because in the
Mm-hmm.
world of lattices, this operation join means basically if you if you take two elements and you apply this join operation to them, then they will return the least upper bound if there is one. And so a joined semilattice is something where any two elements in the ordering have a least upper bound. And
Maybe we should try to draw a picture in our listeners' mind. This is going to be pretty hard, but imagine a graph that's shaped sort of like a spinning top. I'm talking about a graph like a computer science data structure, right? It's shaped like a spinning top. There's a point at the bottom. There are nodes that sort of fan out to a wide point around the whatever the mid hemisphere, the equator line of that spinning top. There's nodes in there. And then they get narrower as they get up to the very, very top of the spinning top, right? And there's just imagine that you could represent a spinning top as a bunch of nodes in a graph. And there are lines connecting every layer, right? So the very bottom point talks to, it connects, it's got edges to every node above it. And every node in each layer has connections to every node above and below it. And that very, very top point of the spinning top in the semilattice is the join or the least upper bound. And that is the convergence. If that graph represents the state of our data, in our case, it's like I'm counting how many users are actively using the website. The CRDT paper says for this to work, the state has to grow in such a way that it always goes up monotonically and always converges on a single point at some point in the future. It's eventually going to reach a least upper bound. I saw this really great blog post where somebody talked about this counters and they had the lattice image and they had these Lamport diagrams. And I saw the lattice image and I was like, light bulb. I get it. They're talking about I understand now. I don't know how to describe a semi-lattice in words, though, Mike.
it's a somewhat tricky concept, but I think one thing to note is that you can have ordered sets where there are elements in the ordered set that do not have a least upper bound. The fact that CRDTs require this sort of a lattice structure means that any two elements are eventually going to end up at the same point in the order. So that makes sense to me, and that makes me sort of understand why these things are eventually consistent. But when you switch over to the operations-based thing, they start to talk about what they call causal ordering. And
well, wait. Just want to, hey, I want to stay on the semi-lattices for a second. Just to go back to my analogy, imagining we're counting users on a web application. I've got 3 different servers. If I build this poorly, you could easily imagine a world in which I have no clue if my servers will ever agree on a particular count for a particular user, right? That's the idea of missing a least upper bound. If I build the data structure in such a way that as long as they follow the rules of either whatever operations have been applied or they accept state, if the state's communicated around the cluster, if mathematically they must converge on the same values at some point in their history, then that convergence is a least upper bound. And in the definition of the data structure, I can enforce these properties if it's done right. But done poorly, it's not a semi-lattice because I have maybe server A says, well, there's 17 people using the site, and server B says 21, and server C says, who knows what server C says. And they're never going to converge because they've been adding different numbers in their history or whatever. They just have a stupid, dumb counter. Who knows if they're ever going to agree? How do I make them agree? I can't make them agree. There is no least upper bound for these guys. Therefore, there's no semi-lattice.
It's also conceivable, though I can't think of an example off the top of my head, that there are just certain data structures that can't be treated this way. So there is, as you said earlier, there's really CRDTs are not necessarily universally applicable to all data structures.
Exactly right. I mean, we could come up with some easily, like a regular, like the data structures we typically use in computer programs, a set. I'm going to add stuff and I'm going to remove it. That won't work, right? If everybody has a set that they add, a stupid number that I add and subtract numbers from doesn't work. I can't just add and subtract a single number because I can't prove that it converges. So the data structures they've defined are those that actually you could prove the convergence. You can prove that they form a semilattice. All right, so let's go to state-based and operation-based. So there are different rules for them. This is kind of what you're getting at. The state-based has to form a monotonic semilattice. That's what we're talking about. Monotonic means that it only grows up, right? And the merge operation, that join at the top, has to form a least upper bound. So we've talked a lot about semilattices, and those are the properties of a state-based CRDT. If you cannot demonstrate that your data structure converges at some point across all these different replicas, not a state-based CRDT. So you have to have that. In general, all CRDTs form a joined semilattice, and they're associative, commutative, and idempotent. Idempotency is the easiest one for me to describe. It means, you can apply that operation many, many times and come up with the same result. But like adding a number is not idempotent. If I have a counter and it's at 4 and I add 1 to it, that's not idempotent because it's 5. And if I add 1 again, it's 6. And if I add 1 again, it's 7, and so on, right? So idempotency, how does that work? Associativity and commutativity are about like order of operations, right? Like it doesn't matter so much when I apply certain operations. And my data structure is still
Commutativity in particular, I think, is sort of key here because it implies that the order doesn't matter. A join B is the same as B join A.
Mm-hmm. Well, and that's what's so interesting about this. Like, again, you imagine you got a bunch of servers, they're all trying to do some job. I don't want to have a leader-based system. I want them all to be online accepting traffic, right? Like just a dumb web server or whatever with, with load balancing. And I don't want to have some crazy complicated protocol because all I want is to just do a thing on the server. And then I want to blast out some message into the ether that says, I did this thing. And if it's commutative, it's like, I don't even care when it arrives at the other friends of the server in that cluster. That's pretty cool stuff. When you go to operation-based, though, the rules are a little different. Because if I'm not now sending my counter, right? I have a counter, let's say, and I'm sending it around, and server C goes, oh, server B has this counter that I can merge it with mine in a particular way. I could see the whole state and merge that state. We're not talking about that. We're talking about applying operations. So now the operation is add 1. Okay, how do you do that? Well, in the paper, they say these operations must be delivered in causal order, and the delivery order must exist. And if there's concurrent operations, meaning we can't determine the causal order, then they just have to sort of commute. They have to be applied in arbitrary order and still work. We talked a little bit about causal relationships when we talked about the vector clocks paper. If you go all the way back to Lamport's clocks, 1978, then the vector clocks are like, it's a Lamport clock where every server has their own Lamport clock. And every server knows about all the servers' Lamport clocks. So we've got A, B, and C, and they've got these logical clocks that they keep track of, everything that happens on them. And so you could use those to form a causal order. If server A is at 4 and I think server A is at 2, then I'm kind of behind on what's happened for server A. And I can use these, like the relationships in the vector clock to figure out, oh, this thing that I'm learning about now actually did happen before this other thing. And so what they're saying is if you want to build one of these operation-based CRDTs, you have to deliver the operations in causal order. That sounds a little too hard for me, Mike.
It sounds to me like one of those, like that cartoon where it says, there's a bunch of arrows and then there's a thing that says, and then a miracle happens.
Yeah. Yeah. Yeah.
I'm sure it's not quite that gnarly, but I just feel like the idea of causal order is presented and shown to be necessary, but never really given details on the implementation of it.
Yeah, it's kind of like that. How do you make $1 million in the stock market? You start with $2 million and then you lose $1 million, and there you go, you made $1 million. It's like, as long as you have causal delivery order, these operation-based CRDTs, they're going to work out just fine. but here we are, like, you mean I got to build that to use this? So For state-based, we have to prove that the CRDT that we're saying is state-based, that its states form a monotonic semilattice, a semilattice that only grows, and that the merge computes a least upper bound, that they actually meet, they converge, right? For operation-based, we have to demonstrate that a delivery order exists and that if there are concurrent updates, that those are commutative. This is from the paper on page 14. And they also say, you could actually build or emulate a state-based using an operation-based, and you could build an operation-based using a state-based. And I kind of like this actually because they talk about the gut response I had, and I think you had. They write, state-based mechanisms are simple to reason about. Since all necessary information is captured by the state, they require weak channel assumptions, allowing for an unknown number of replicas, but sending state could be inefficient because it's like these are large objects. So maybe what you do is you ship the changes, you ship the deltas. Oh, but by the way, you got to use op base for the deltas. Like, so easy to reason about. I think we both are feeling that. Like, this is my knowledge right now of the state of the world, and I'm going to send it to you. And we know in advance that my state will converge with your state. Okay, cool. And weak channel assumptions means some random server could just come online and start contributing to, and it's like, rad, welcome to the party. Start telling us your state too, random server. We'll get your changes in here too. No big deal.
Yeah, you can see why it's such a popular idea in the local first world.
It seems like a reasonable way to go if you don't need the kind of consistency that you get with like a Paxos or a Raft. If you're okay with eventual consistency, like, yeah, eventually it'll be true, it'll be cool, everything will agree. It just seems simpler. I feel like I shouldn't use that word. Like, it's a horrible crime to use that word. It seems simpler than thinking about a really complicated protocol like a Raft or a Paxos, like building Raft and the things you might make, mistakes you might make. Knowing first I do this, then I do that, then if this happens, you do that. That sounds harder than like, as long as my data structure converges, I can just blast it all over the place, and I don't even care who participates. I don't even need to know how many nodes there are, Mike.
It seems like these are often also used in conjunction with other consensus mechanisms. So I think Redis, for instance, has CRDTs. Mm-hmm. I don't know that I've ever intentionally used them, but I'm pretty sure they're in there.
Yeah, something with our active, like 2 active servers, I think, is how they do that.
There used to be REAC as well, RAAK, which is a pretty generalized, pretty general database that was using CRDTs pretty thoroughly.
So they do say specifying op-based, like we keep responding to, like it just sounds hard. It's more complex because you have to reason about the history of the operations, but you can express more with operation-based, they say. And the payload's simpler because you're just sending, do this, do that, do this, do that. But op-based replication requires reliable broadcast, and you also have to track how many members of the group you have. So I don't know about you, Mike, but I'm reading this paper like, I'm going to pick state-based from the salad bar today, and I'm going to sort of like know that op-based exists and probably try to avoid. But my state could be large. Okay, how are we doing so far? Is this a mess? Are we making a mess of it? Is it getting clearer? Are we getting through the fog?
I guess that's not a question that we can answer. Maybe somebody will give us feedback and say, I still don't understand.
Yeah, you guys are messing this up. Well, maybe we should talk about the examples. So the comprehensive paper has a whole bunch of examples of specific CRDTs. And this work actually showed up in relation to collaborative text editing. When it's like you look at their examples, and I don't know about you, but I'm like, how do you turn that into collaborative text editing? So they have the G counter, the grow only counter. You cannot subtract the G counter. Everybody has a count. And how do you do that as a monotonic semilattice? Well, if you got 3 servers, every server has its own counter, and the state is what I know about my counter and what I know about your counter and what I know about the other counter, the other third server's counter. And when I share that with you, and merging those together is just adding all the numbers up. And right, like so, or taking the max, I guess, right? Not adding them all. And then the total state is adding them all together. And then what if you wanted to subtract? Well, they're like, you can't just add and subtract that single counter, you need two G counters, one for adds and one for decrements. What's the current state of the world? It's the adds minus the decrements. But both of those only grow. And so an operation-based version of that is like operation happened with a vector clock. And so it's like you're kind of transferring that state into the vector clock. I had this many operations, so you can figure out what the ordering is of the operation. Am I helping with operation based? Maybe I'm doing a bad job there.
Yeah, I think you're helping, but I think maybe you could elaborate a little bit on the vector clock. I know we've talked about it a dozen times in various contexts, but going back to at least our initial talk about Lamport, maybe explain a little bit what that means.
In Lamport has that wonderful paper that we talked about that I tell people to read all the time. It's called Clocks. I can't remember the name. It was just a Lamport Clocks paper from 1978. Great paper, super fun to read. There's this rad moment in it where he's like, yeah, you can't do that because of special relativity. He's like, look, we got different servers. One might be in Ohio and one be in Florida. One might be in Colorado, California, whatever. You can't look at wall clock time and trust it to know when things happened in relation to each other. You can't just start a monotone clock on each CPU. That's obviously not going to work. You need some sort of way to say, what's the comparative time between the one in California and the one in Ohio? So what you can do is every time those servers receive an event, they start with this thing called a logical clock. It's just a number, but an integer. It only grows. It's set 0. Every time they receive an event, they add a number. Every time they send an event, they add a number. And so each server has its own number. And those numbers track events. And the interesting thing is, with those numbers, you can establish what Lamport describes as a happens before relation. Now, this is a partial order. I know that's one of your favorite topics. You can't look at the number on every server and necessarily compare it to every other server. Some things are concurrent. You can't say A definitely happened before B. But in other cases, you can say, C definitely happened before D. You could build this relationship. Now, that's not really that strong. It doesn't give you a causal order, right? Like A caused B. You don't really know. You just know that A happened before B or it's either A happened before B or I don't know, in which case we call them concurrent, right? So you got two options. A happens before B or I don't know, concurrent. To establish something called causal order, researchers in I guess it would have been 1990, that 90 paper, 91 paper. We read that long paper. They talked about vector clocks. And so now I have a Lamport clock for me, but I actually also keep track of vector clock for the other servers too. I keep track of the Lamport clock for the other servers too. So I've got 3 servers in my cluster. Each server has 3 Lamport clocks, representing its own state, first of all, and the states of the other servers. State, in this case, being that logical clock. So that's a vector clock. Now, I can say when I receive an event, if that event includes a vector clock, I can compare it to my vector clock. And in a lot of cases, I can establish, maybe not a lot of cases, but in some cases, I can establish which one definitely preceded the other because it's in the vector clock history of my vector clock, right?
So
again, I'm only
dumb it down for people like me. So every server has its own vector clock, and when it broadcasts a message to the other servers saying, here's an update that I make, it also sends along its vector clock. And so the servers that receive that message can see what your clock says, what that server's clock says respective to their server clocks, their vector clocks.
And there are rules. So like if this other server sends its vector clock, I'm always going to trust. I'm going to trust whatever the highest number is, right? Like, okay, I got a message about server C and it says its vector clock is 10. I thought it was 9, but it must be 10. I mean, I'm not managing that server's logical clock, its Lamport clock. And so in my vector clock for that server, I put that number at 10. It's 10 now. I didn't increment. I just saw from the information I'm receiving from the other servers in the cluster, that clock is 10. Now I got an event, so I'm incrementing my clock. And when I send events, I'm going to include my vector clock, which includes my clock. And other servers are going to know, oh, Eric's server is now at this number. And we can use this, oddly, surprisingly, maybe, to describe a causal order of events. So you can kind of look at things that are getting sent with these vector clocks and use the vector clocks to put them in a kind of order, not necessarily the canonical answer for everybody for all time order, but an answer, a causal. This may have caused this. This
So the
preceded
objective again is to sort of enforce an ordering. So if you have only one replica, then the order is kind of trivial. But since on a distributed system, the ordering can get kind of weird, and as Lamport showed, you can't really rely on wall clock or system clock time. Then you need something to enforce this ordering, and that's essentially what the vector clock is trying to help you do.
But you will still have quote unquote concurrent things happening, things where you cannot determine the causal order. And when we go back to these operation-based CRDTs, they're like, well, when you get to those, it has to be a thing where you can apply them in any order. It has to be commutative. Otherwise, it's just not going to work. You're going to end up with weird inconsistency. We're going for eventual consistency, okay? Follow the rules, you will get eventual consistency. So here's some of the other data structures they describe in the comprehensive paper. So they've got the grow-only counter. They've got the positive-negative counter, PN counter, right? That's two grow-only counters, one representing increments and one representing decrements. They've got the grow-only list. They got this thing called the multi-value register. That one I struggle with a little bit. They've got the grow-only set. They've got this thing called the 2P set, where you can add things to it, and then you can remove them. But after you remove them, you can't ever add them again. They do that with the grow-only set plus a tombstone set. And then there's these like variations on this. There's like an add biased one. There's the remove biased one. They build these graphs. They build a map. They build this thing called a monotonic DAG. And if you're like me, you're looking at that like, what can I build with that stuff? They have this description of peer-to-peer text editing is like it's like add removing, right? So when somebody is editing a document collaboratively, that person is adding things or they're removing things, and that's it. So it's like this add remove graph in a way, right? So they're like, yeah, we use CRDT for this, and then edits never conflict; they always converge, even for people who are disconnected for long periods of time. That sounds pretty cool.
Yeah, it's a very nice idea. I wish it worked for everything.
I kind of, yeah. Don't you have this like gut feeling like, can you just make like arbitrary data structures that I could have this agree? That's how I felt too. It was like, oh, wait, so, okay, if I can build what I want on top of a G counter or a PN counter or a grow only set, then I'm cool. But unfortunately, there's a lot of problems I want to solve that require stuff that's not that. I want to remove things from data structures. Mike, I want to subtract numbers. I really miss being able to subtract. Subtraction is a feature I really like in math.
Yeah, it does come in handy occasionally.
So where does this appear? You mentioned React. You mentioned Redis. Cosmos DB, Azure's document data store. They have this last rights win CRDT, LWW. That's another one described in the paper. SoundCloud uses this. They have this thing called Roshi, a CRDT system for timestamped events. The Roshi GitHub repo is pretty interesting, actually. In Akka, the event streaming, so what is it? How do I describe Akka? They have this distributed data CRDT that's embedded in there, and FlyIO recently released this thing called CRDT on top of SQLite. So it's like a bunch of SQLite nodes. They gossip state around using CRDTs. And they built this for service discovery. So like I spawn a new thing and it wants to figure out where's my database. And so it talks to this service that they call Corrosion. It's a pretty metal name, isn't it? It's called Corrosion. And Corrosion is this cluster of machines that use CRDT to communicate with each other and SQLite to persist their data. And they do this in a gossip based system. So it's just like, something happened. I'm just going to blast out random nodes to tell them. So peers is kind of all over the place. People write about it all over the place. Here's my question for you. CRDT is really popular. Tons of research in the last 15 years, like blog posts, people in industry talking about it. It's used in all these projects. Here's my question, Mike. Why so popular? Why do you think?
Probably for the reasons that we already mentioned. They, in the cases where they work, they're definitely a simpler solution than generalized consensus protocols.
You think it's fair to call them simpler? I mean, you got to know semi-lattice least upper bound probably, right? To build the state-based CRDT, right? Is that simpler?
Do you though? I mean, really, you just kind of need to know that you can do operations in varying orders and end up at the same place at the end.
Yeah, I guess if you're not inventing one, if you're just like, I'm going to use the G counter here, pull that G counter off the shelf and start using it.
I see, like in the case of local first stuff where you don't have access to the network, it seems like a really almost essential feature of those things. I think in the more general distributed system case, I think it's probably just simpler than reasoning about other protocols.
I think so, but I have kind of a gut response about what that simple. I feel the same way. I feel totally the same way, but I have this intuition about why we say it's simpler. And here's my thesis for you. I think that when you look at a Raft or a Paxos, to build it correctly, you have to code a protocol that has many steps. It's like it's complex and it's messy, maybe, or it seems messy. And there's something funny about protocols. I think that it's harder to build an intuition for a protocol, which involves a sequence of steps, than it is for a data structure. Like a data structure, somehow you get it written down in in your text editor, and you could just sort of see what it does. It's flatter than a protocol. And maybe that flatness, maybe my intuition has to do with time, because a protocol has to always be aware of timing, of this happened, now this has to happen. This is going to happen. And if that happens, then this happens. Whereas a data structure is stupidly like, I am data structure A, and I've received a copy of myself as B, and I got to figure out how to merge B into A, and boom, my job's done. Doesn't matter when it happens.
I think there's also this kind of nice symmetry to CRDTs. So with other more complex consensus protocols, it always feels to me like you're kind of starting out saying, okay, I want to do distributed computing to solve certain problems that these systems are going to have. But I also need to designate one of those systems as being sort of the leader, or the one that's really keeping track of things. And I think there's something unsatisfying about that, especially because of the hoops you have to jump through to make sure that there is a leader and that the leader stays alive and things like that.
Yeah, I think it's the hoops. It's the protocol, right? It's the remembering when we're in this state, then the action we have to take is action C, and then we will try to achieve this next state. It's way different than thinking in terms of data structures. And we're talking again about eventual consistency. We're not talking about linearizable consensus. So maybe it's not a fair contrast to compare to Raft of Paxos, where it's like they're doing what I would call hardcore consensus. I don't think the word hardcore shows up in the literature, but that's pretty hardcore what they're trying to do. And often in the apps I write, if the stuff's kind of stale, like, yeah, maybe the number that I'm showing on the website for the counter of how many people live, maybe it's not quite right. But if I have a guarantee that eventually it's going to be correct, just refresh the page a bunch. It'll get there. That's pretty cool. Like, that's good enough for a lot of my work. And the failure modes of those other things are so complicated. Just reasoning about like, okay, if I have this many nodes, I could tolerate up to this many failures. That's really complicated. and even like tracking like who's in a failed state right now, and and like the idea that I could just have arbitrary servers spin up, like oh, the load is really high. I'm just gonna add more servers to my thing. I'm gonna auto scale them. That's pretty cool, right? Again, that's a state based thing. Like they just seem pedestrian in a way. That's not the word I want. They seem more achievable for just an everyday programmer than like building a Paxos or even building a raft. I mean, yeah, we could build raft. A lot of people build raft, but build raft, validate it, make sure it works, make sure that you're aware of when the cluster's in a failed state. This just seems, I hate to use the word, but way easier.
We should write an archive paper called Hardcore Consensus.
I do not want to. I actually found, there was a paper in 2012, which I found because I was like looking at other work people have built on top of CRDTs. And there were a group of researchers who were talking about how you can actually achieve linearizable consensus on top of state-based CRDTs. But turns out that what they actually built was state-based CRDTs. Oh, and by the way, when you want to know what the current state of the world is, we're going to do Paxos at that time. They call this CRDT Paxos. And they're like, well, reads are updates are immediate. You send an update in, boom. You want to know what the state is? Give me a second to think about it. And that give me a second to think about it is I'm going to go through a whole Paxos thing to make sure we all agree on what the state of the world is. And then boom, I'm going to give you an answer. So CRDT's Paxos. So you can bake on more complexity and get to linearizability. And they actually talk about this thing called lattice agreement.
Ooh.
Lattice. So if you could like get lattices to agree, then you can achieve a kind of consensus.
I think hardcore consensus makes more sense than lattice agreement.
So CRDTs, I started out like, that sounds complicated. I don't really want to get into that. And then I got into it and was like, wow, I can see why people are attracted to these things. They do seem a lot simpler than consensus protocols. But then there's a couple of, like, there's a rub in there. One, you can't just take any arbitrary data structure and make it a CRDT. You have to use these defined ones or come up with others that formally follow the mathematical properties required. Oh, and by the way, if you want to use operations, instead of just sending this, whatever your data structure is, you don't want to send your whole data structure? Great, use operation based. Oh, but by the way, you have to ensure that those operations are delivered in causal order. So I don't know, Mike, maybe what we're going to end up with is a number of users on the website that has no bearing on reality. Who knows?
I suppose it doesn't really matter.
It matters to somebody. Actually, here's what we could do, Mike. Let's just use a database. The database will solve. I'll put the number in the database. I want to change it. I'll start a database transaction. What could go wrong, Mike?
Maybe instead of using distributed systems, we should just get one bigger computer.
Oh, yeah. Yeah, that's a good idea. We'll just get one giant one, and we'll put it in the middle of the planet so it's close to everybody.
I like it.
So that was my sojourn into CRDTs. I enjoyed reading about them, and they're sort of like baked into this underlayer in my brain now.
It's a good name, too. Conflict-free replicated data types.
I like that. Yeah, I'm a low conflict kind of person.
Conflict-free is a nice thing in this day and age.
I think the analogy to Dawn of the Dead, I don't know, it feels like the beginning of that movie is so weird. I don't even know what happens, right? Zombie movie. There's these ragtag group of people. I don't remember why they are together. They're all in a helicopter, like a news helicopter. They fly around. They see the mall. They're like, that looks like a defensible space. They go and they live in the mall. The mall here is like the CRDT. It's going to protect us from the zombie hordes of distributed systems problems, Mike. We got this. We got a movie theater. We got the popcorn. We got the food court. We got clothes if we need. We got sporting goods if we need. We could live here for years, Mike, in the CRDT mall, and very high walls, very defensible space. I think
and the only downside is that something might eat our brain.
They got to get in first. Those distributed systems problems, they've got to pierce the wall, and then we're screwed.
Have you been to a mall recently?
I've been to an outdoor one that's close to my house. I went there this week because I kind of wanted a sweater, but I did my typical shopping experience where I went to the mall, I had some coffee, and then as I tried to build motivation to go into a store to buy a thing, I felt my motivation withering, and I turned around and I went home.
There's an indoor mall not too far from where I live, which is kind of an odd thing for Southern California, believe it or not. And I don't think if I were flying around in a helicopter trying to get away from zombies, that would be my first choice anymore.
I think what you're saying is when you go to the mall, there's already zombies in there. That's what you're subtly saying
Yeah,
to me
I think you would
here.
have a hard time distinguishing the zombies from the regular clientele.
Okay, we will not name this mall. All right, Mike. I think that's good for us this week. So this has been Picture Me Coding. As always, if you would like to support the show, we do have a Patreon. $4 a month subscription can help us produce, edit, and make the show and continue pouring our voices into these microphones, talking about these computer science problems. We're also on Blue Sky at Picture Me Coding. And if you'd like to email us, you can send us an email at podcast@picturemecoding.com. My name's Erik Aker, my co-host Mike Mull. We will see you again soon.
See you next time.